Okay, in this lecture, we're going to look at beams. And if you look at the Canvas module, you will see that beams is 5 weeks, right? So it's almost half the strength of materials course is beams, right? And why is that? Right? Beams, we see here, beam is the most important structural element. You look at mechanical, aeronautical, civil engineering, even aerospace engineering, right? A beam can be defined as a structural element that is long compared to its cross section. So if you look at, for example, if you're in class or you look at your desk, you would see that you have these long members that spans a certain distance. And it would be fixed most likely or supported on both ends. So that is a beam. Right? And you could look around the room here right now and you would see plenty instances of beams. And that is why it is so important because it's so common. Right? Your curtain rod, for example, is a beam. Right? Now, we're looking at this beam here, right? And the gray portion is the beam, is the structural element, and the ends here is called a supports. Right? Now you notice one is circle, one is round. Right? So this here is called a roller support. Right? Roller support meaning that it allowed this ends here, it will allow this end to move back and forth or roll on it, right? Another way is represented sometimes is like this. So sometimes you would see it looking, this is a beam here, it will look something like this. Right? On this end here now, we have what we call a pin support or pinned. Right? So this would allow rotation like this, right? Or pivot. Right? It cannot go left and right, it cannot go up and down. Right? These types of supports, or what we do on the end, we refer to that as boundary conditions. Boundary conditions, right? Or sometimes you would see B, C, and small s for short. Right? Because again, these conditions are only boundary, right? The ends. And when you apply load on a beam, of course, the beam would sag. So if you take a ruler, right, you could actually bend the ruler by putting a load in the middle, right? So that is how the beam deflects. And we will go on to the calculating a deflection later on in this 5 weeks. Right? So that brings us now to how we could solve for these beams and what we're solving for in these beams. Right? So to begin with, we're going to look at or talk about something called statically determinate beams. And statically determinate beams means that we could solve it. We could solve the beam, right? So I'll just just kind of expand that a bit here. Right, so I'll open up a page. So if you have a beam, we have a load in the middle here and it's supported. Right? We would have some reaction forces being applied here. Right, so this would be R1, this would be R2. P could be equal to, say, 10 kilonewtons, for example. So we know P, we have that. What we don't have is R1 and R2, right? So how can we solve that? So the first thing we could do, we could say, we call this point 1, point 2. We could take moments about point 1 and say that's equal to 0. Right, that's one equation. We could also sum the forces in the vertical direction and say equal to 0. Because we have equilibrium, those things will be equal to 0. Right, and this will be equation 2. So now we have two equations and two unknowns. So therefore, we can solve now for R1 and R2. Right, and this is what we call the beam being statically determinate. Because we could determine the unknown forces and moments in this beam. Alright, so if you want to continue to solve this, we could let's take equation 1. Alright, remember to take moments. Moments is force by distance. So we're taking moments about, let's just take moments about 0.2, just to keep a consistency here. Right? We could call these distances L12, L12 because the load is in the center. Right? So it will be P multiplied by L12. Right? So that if we take moments about 2, that will be going like that. Anti-clockwise is positive minus R1 by L. Right? As R1 there, and R1 is be clockwise, so it'll be negative. And so we sum the moments and we see that is equal to 0. So that means you could solve for R1. Right? So that will be P on 2, which is expected because the load is in the middle. Right? So this is from equation 1. So the next equilibrium condition is the sum of the forces in the vertical direction is equal to 0. So what we could do, we could say R1 plus R2 is equal to P. So R2 is P minus R1. P minus P on 2, which is, of course, P on 2, which is what we expect. Alright, so the forces now on this beam will be P on 2, P on 2. Right, so that is what being statically determinate means. Right, now you notice the beam was drawn. I'll just go back up here. The beam was drawn with a triangle. Right, so let me just be a little clearer here. That is the beam. We had a triangle on both ends. Right, and that triangle means that it's simply supported. Right, so the beam is allowed to rotate on that end. Right, so if you were to kind of draw the deflection of it, let's just kind of exaggerate the deflection. You'll notice now that the point remains the same, but the beam has now rotated about that point on the end. So if you notice, the beam started off here, now it rotated up in a way. Right, so there's zero moment. There's zero reaction moment, meaning that there's no moment or nothing that is holding or preventing the end of the beam from rotating. So it's free to rotate. So that's what we call simply supported because it's just resting there. It's simple. Right, if you look at a fixed-ended beam now, right, so I'll just do another page here. Right, so if you look at a fixed-ended beam, and we represent a fixed end by doing these lines here. Right, so we're kind of looking at that, we're looking at it as the beam is cemented within the support in the wall. Right, so the ends in this here now are not free to rotate. Right, so the ends not free to rotate here, as the case with the simply supported. So in this case now, we're going to have a reaction R1, R2. Right, remember we have this load here, P in the middle. And in addition to that now, remember the beam in the previous case was rotating up. Right? Now the beam is not rotating up on the fixed end. So that means something is preventing it from rotating. And that prevention, or what it is causing to prevent it from rotating, is a moment, a reaction moment. Right, so that reaction moment is like this on both ends. Right, so if you were to kind of draw this beam now being deflected, it will look something like this. Right, so that would be the deflection shape. So you notice the ends now remain fixed. It still kind of have a little straight portion here. And that's because this moment now is bending it back, we could say. Right, so our equilibrium equations were what? We take moments about a point equal to 0. We sum the forces in the y direction equal to 0. And well, that's it. Right, so we have two equations. 1, 2. we have two equations, and we have how much unknowns? We have the two reaction forces and we have the two moments. We have four unknowns. Right, so if we have two equations and four unknowns, then we cannot solve that. So because it cannot be solved, we say we have a statically indeterminate beam. Because we cannot statically determine those reactions. So we have a statically indeterminate beam. When we go on to year 4 and we do finite element analysis and stuff, we would see how we could solve these equations. But for now, using the concept of the strengths we're going to do in this semester, we will not be interfering or going into any fixed end beam, or any, I should say, any statically indeterminate beam. Right, so remember you could pause along the way, take your notes. Right, so we just went through all this here. Right, these are your equilibrium equations. And well, this is a recap of the moment of a force by distance. Probably should have went through this before we took moment, but we all would know by now how to take moments, right? And we spoke about supports. We spoke about roller supports, pinned and roll on one end, right, and how your free body diagram would look. Right now, you see we use the term free body diagram. I'll just take a step back here. A free body diagram is a diagram that has a diagram of an object that has just the forces are being applied to it. Right, and that is what we did over here. That is what we did here. In that we had a beam and we had two supports, and the free body diagram FBD would be the beam with just the forces being shown. So that's what a free body diagram is. Alright, so for a cantilever beam now, obviously for a cantilever beam, we can't have a pivot at this end here because it will just pivot down or swing down. So a cantilever beam is where the beam is free on one end and is fixed on the other end. So of course we're going to have a reaction force to counteract F, and then we're going to have a reaction moment, something to counteract the moment due to this F here. And in this case here, if we take moments about a point, and then we solve the forces or we resolve the forces in the vertical direction, we're going to have two equations. But in this case here, we're going to have just two unknowns. We're going to have the reaction force here, and then we're going to have the reaction moment. There's nothing on this side. Right, so you're going to have two forces and then two equations, or two unknowns, two equations. So this in itself is a statically determinate beam, right, even though one end is fixed. Right, the next thing I want to move on to very quickly is identifying beams and components. Right now, in engineering design, when we do engineering design next semester, you're going to have to be able to identify what components in your design are beams. So then we could extract it and analyze it. Right, so again, we're looking for elements or structural elements that are long compared to the cross-sectional area. Right, so in this case here, if you look at this hydraulic lift or whatever it is here, we have a spring. So the spring now would be in the center here. We have a hydraulic cylinder here. So we have a force pushing here. Alright, so I'll just draw that arrow showing the force. We have the spring now that will be preventing or trying to hold back this beam here. Alright, so we have a force pulling back here. Right, so this over here is a pivot. This here is a pivot point. This here you could regard as a pivot point too, but that is where the spring is being applied. The force is being applied. So now if you look at the beam, we cannot draw it horizontal. So it's always good to kind of turn our beams horizontal. We have a force on the end here, we have a force here, and then we would have some reaction force in the end here. Right, so the reaction force direction is not really how we draw it is not really important because when we're working out the maths behind it, then the maths will take care of the direction. Meaning that if we say that we draw it down and in resolving we use the up as positive, then if the answer we get is positive, well then it was in the correct direction. If it's not, well then the direction is the opposite. Right, another example here, we have a prototype landing gear, and what is shaded blue here is the beam we want to identify. Right, so after the wheel has been retracted, this is the beam here. So we could approximate now the weight of the wheel on the end here, so that will be a force acting down. We have some structural element holding up the landing gear, so there's a F2 here. And then we have another structural element here. We could just assume it to be in that direction. Remember, again, we just drawing arrows here. We don't really concern about the direction. And then we have a pivot here. So that will be a reaction force. Right, so that's how we identify beams. Right, so what you could do, you could go around the room or look around and try and identify a beam, be it on a table or a chair, window pane, or even the structure of the building, and identify the beam and see if we could mimic the forces on it. Right, kind of draw your supports and the forces and reactions on it. Right, so the next thing we're going to go on to is shear force and bending moment diagrams. Right, so what is a shear force? What is a bending moment to begin with? Right, so if we look at this beam here, this is again a simply supported beam. Simply supported meaning that there's no fixed ends, there's no reaction moment. It's just simply supported on two pin joints. Right, so if you look at this beam, and you can see we have a dotted line here. Right? So that dotted line represents a cut in the beam. And why are we cutting the beam for? We want to kind of get an imaginary look inside the beam. That is why we're cutting the beam for. Right? And why we want to see inside the beam for? And we want to kind of get a visual or understand what is keeping the beam together. Because if we have a load applied here in the center, it's pivoted here, so we know what is keeping the ends up. But what is keeping this section up and preventing it from falling through? Right? We must have some internal mechanism, internal forces and stuff keeping it up. Right? So if you want to draw, let's say we want to kind of do a section inside here. So how we cut the beam. Right, so that's the cut surface. Right, this is the pivot on the end here. Right, so this is just the cut surface, right? If you were to look inside this beam, right, this cross section, and let's move that there, you would see that we must have some upward forces that prevents this chunk of beam from sliding or sliding or breaking away from this chunk of beam. Because here we have the force acting down, here we have a force acting up. So inside here now, we're going to have two surfaces that are going to be want to slide over each other, right? And we call that sliding force, if we could recall from the introductory lecture, forces that slide over each other or that is parallel to a surface, we call that a shear force. So inside the beam, a shear force exists at preventing one chunk of section from sliding over from the next one, right? So that shear force must be able to counteract whatever external force being applied. So that is shear force. And that will give rise to shear stress if we divide it by area. The next thing we're going to look at is what is preventing the beam from twisting away. Right, so we remember that the beam deflects like this. Right, so in that deflection, there are moments that is causing that turning effect. Right, if you look at a ruler, you try to bend a ruler, the ruler, if it's bend the ruler, it would look like this, like the deflected beam. So what is causing this beam to have this slope then? This twist? You must have a moment doing that. And that moment now exists inside the surface. So we would have a moment looking like this. That is twisting the beam. to cause it to give it that deflection. And that is called a bending moment. And the term bending moment meaning as a moment that causes any beam to bend. Right? So that is what happens inside the beam. And if you look at it in 2 dimensions and we cut the beam, this is what we will get. Right? We have our shear force and we have our bending moment. Now we know that the beam is in equilibrium. Right? So if the beam is in equilibrium, that means all the forces, if you draw a free body diagram, the forces and the moments must cancel off each other. So if we just take this here, if we call this V for shear force and we call this M for bending moment, we could do something. We could take one direction moving forward to make life simple. We could say down is positive, anti-clockwise is negative, positive. Right, so this could be our orientation of what positive is. Right, and we know that now if we take moments, or should I say, yeah, if we take moments about the surface and we some forces about the surface, then we say for equilibrium, all these things must be equal to 0. Right, that's the sum of the forces and the sum of the moments about that surface. Right, so just quickly we could say, okay, sum of the forces equal to 0. Right, and we know we go in that down is positive, so we could go minus P on 2 plus V. Right, remember this here is V is equal to 0. So that means the shear force is equal to P on 2. I remember P on 2 is a reaction. Next up is the sum moments. And we say the sum of moments equal to 0. So we take moments about the surface here. Right, so we take moments with P on 2. So P on 2 about that surface, that will be going anti-clockwise. Clockwise. So be minus P on 2 times LB. Right, M is anti-clockwise on the surface is equal to 0. So your bending moment, therefore, is minus P on 2 LB. Right, so that is your bending moment and your shear force about that point. Right, so we're going to look at this example and draw the bending moment and shear force diagrams for this beam. Right, so the first thing we want to do is determine the reaction forces. Right, on the beam. So that way we have all the forces on the beam. Right, so in this case here, we know that RA and RE is 500. And why? It's 1,000 newtons acted in the exact center. So obviously load is equally divided. Right, so that's why they gave it as 500 already. There's no need to do any calculation for that. Right, so we have RA and we have RE. Right, and what we're going to do, we're going to find the shear force and bending moment values at all the points A, B, C, D, and E. So that's what we're going to do. Right, so we're going to break the beam at these different points. Right, so we start with point A. At A, we know that A is a free surface. And what that means is that if we look at the beam, we have our A's over here. We have a free surface here. And if you have a free surface, like for example, the edge of a table, there's no forces really being applied, even though we may have internal forces. Because it's a free surface, there's no force being acted upon on that free surface. Right? So we could say that the shear force at A is equal to 0. Now remember, we do have a reaction, right? And we will have a jump in the graph at that point, and we will get to that just now when we actually join the graph, right? Now again, we talk about simply supported. We talk about having pivots. So this is the beam. Rotate at the end. So if it's allowed to rotate, it means that there's movement to prevent it or hold it in place. So the bending moment at the free end is 0. So these are our value on the graph for shear force and bending moment. The next point now is at point B. Right? So if you look at the diagram, that's here. So what we do, we draw the beam up until from one end, so we have RA. So we draw up until point B. And we draw our shear force and bending moment directions. The positive directions. Remember, down is positive, anti-clockwise is positive. And we know our distance is 0.5 meters. Right, so we could calculate VB and MB. And that's like what we did in the singular case. Right, we sum the forces in the vertical direction. So we say, okay, we could say minus 500 because that's R reacting up, plus VB equal to 0. VB is 500 newtons. So that's our shear force value at B. Bending moment, we could take moments about B, make it equal to 0. Right, so minus 500 by 0.5. Right, so that is this force by this distance, and the entire thing is removed. Well, the moment is clockwise, so that's why it's negative. Plus MB equal to 0. So MB is 500 by 0.5, which is 250 Newton meter. Remember, always remember your units. So those are your values for shear force and bending moment at B. Next up, we go to C. Right, so the next point is at C. Now you notice C has a force, has the force acting on it. Right, so remember this was B here. Now we at C. We have the 500 Newton force, and our distance is 0.5, 0.5, according to the diagram. Right, we also have our acting force, our applied force at 1000 newtons here. We have VC, MC. Right, so in analyzing this now, right, now we have 1000 Newton force being applied here. When obtaining, I make a note here. I remember you making your notes as you go along too, right? Right, so when you applying the shear force at a point of loading, as in this case we have the 1000 newtons here. First, you want to ignore the load force, right? Right, so this is a kind of a shortcut method, or should I say a method that will assist us in drawing the diagram a little better. Right, so we could say the shear force minus 500, because up, plus VC equal to 0, so VC is 500 newtons. Right, that's at point C. But we need to consider the load now. So what we could say now, when we join the graph, we could say down on the graph by 1000 on the graph. Alright, so we draw in this graph, it will be 500, and then we move down by 1000. So that will take us to minus 500. Right, if we had put in plus 1000 here, then the value for VC would have been minus 500. Right, so you could try that and see. Right, so at C, we have already two values of shear force. We have 500 and minus 500. Alright, next step going up is with point D. Alright, so at D, alright, so along every point of the beam we taken, there's no need to draw this. I'm just doing this for explanation's sake. Alright, so this is B, C, this is the force here, and this here is D. Right, distance is 0.5. Alright, so at point, no, we didn't calculate the bending moment. Alright, so it will be, I didn't calculate the bending moment, so it will be minus 500 by 1 plus MC. Remember, we take a moments about point C, so the 1000 newtons wouldn't have any distance to multiply by, equal to 0. So MC is 500 Newton meters. Alright, so back to D. Alright, so again, VD, MD. Alright, those are the positive directions. Alright, so for now, you could write this little thing every time so that you become used to understanding and knowing what the directions are for beams in terms of positive and negative. Alright, so it will be minus 500 plus 1000 because it's down, plus VD equal to 0. So VD is minus 500. Alright, the bending moment, again, it is upward here by this distance. So, and that is clockwise, will be negative minus 500 by 1.5, 0.5. We have this here, that'll be positive, plus MD equal to 0. Alright, so MD is 250. And then we have finally at point E, and that's the end. Alright, so there's no need to do this one, and I'll show you why. First of all, if you were to find the shear force, it will be free surface, right? So it will be minus 500 plus 1000 plus VE. So VE is minus 500, right? And then remember we have that upward force being applied here. So then you go up on the graph by 500. So if you minus 500, you go back to 500, then you end up at what? 0. And we know at a free surface, right, the shear force is equal to 0, right? For bending moment, Again, it is a free end, a pivot end, I'll auto it so the bending moment is 0. But if you want to show that this as a check, we could say, right, the stake moment, this distance here would be 0.5 by, this is 2 meters. This distance here would be 1 meter. Right, so remember our directions. So minus 500 by 2. Alright, so that will work out to be 0 as expected. Right, so this is always a check to make sure that, calculation is correct, the distances are correct and stuff, reaction forces are correct. Alright, so if we need to draw this on a graph now, alright, so if you need to draw this, alright, so you start off with your beam, you start off with your points you want to, know the values at, and you can just draw some guidelines. Alright, so this is A, B, C, D, and E. And then you draw the axes. You come like you're really drawing a graph, and you're drawing your graph along the x-axis is your distance, the y-axis is your value. So the first one is shear force, right, or V in newtons. So we know this was 500. So it was a free surface. We say free surface is 0, and then we go up on the graph by 500. Right, so the whole up on the graph, down on the graph, at a point we could come back here at point A and say, okay, and up by 500 because we have the area force being applied here, right? So we start off at 0 and then we go up by 500. So this here would be, we'll zoom in, this here would be 500, that value there. At point B, the value is 500 also, right? So we go straight line. At C, it's 500 also, so 500 again, and then at C we said that, and down by 1,000 on the graph. So we go down by 500 and then 500 again, that's 1,000. So this here is minus 500. Right, and then this entire drop here is 1,000. Right, at point D, the value for shear force was again minus 500, and at E, minus 500, and then we said it was up by 500, so it goes back, go up on the graph, brings it back to 0. So this here is our shear force and bending moment diagram. Well, shear force diagram, we haven't done the bending moment diagram. So that's our shear force diagram. Right, the next one now is your bending moment. So on the same sketch here, we could draw another axis, and we will call this bending moment. Units again, so units is always important. And then we start. So at A, we know that pivot end, MA is 0, and MB 250. Right, so 0, this is 250, right? 250. A, B, let's write in these things here so we can know what's going on. At C, the value for bending moment is 500. Click on the bottom there. I just kind of join a straight line here so you know where. Right, so this is 500. At D, I believe it was 250 again. Yes, 250. And then E is 0. Right, so this here is 250. Alright, so this is our bending moment diagram. Right, so why are we doing this for? Right? So graphically, we know it's easier to spot things graphically. So in a graph like this, if you are trying to analyze some complex beam, a ton of forces on it, all over reactions, etc. Going through a table of trying to of all these values might be a little cumbersome, but if it's plotted or drawn, you could glimpse it and say, okay, well, the maximum value is here. So the maximum bending stress, which we will come to, the maximum stress would be in the middle, which makes sense, right? The middle of this span here is where we will have the higher stress. Similarly with shear force, we know that this jump here is where the beam experiencing a high shear force, right? Something to note here, let's pay attention as you move into the other weeks. If you notice where this line crosses 0 is where we had the maximum. Right, so where shear force is 0 most of the time, or all the time I should say, your bending moment will be at a maxima or minima. Remember those terms? Maxima or minima. So 0 here says at a minimum. 0 here is at a maximum. Right, so that is how we plot a shear force and bending moment diagram for a simple case. Right, where we have, there's some terminology, where we have a positive bending moment, we call that sagging. Right, because this value is positive 500, and where we know that the beam is sagging over there, right? If we have a negative bending moment, we call that hugging, meaning that the beam is bending in the opposite direction. So if for example, we had a beam upside down, I should say, then this will deflect like this. So once we have that reverse deflection, we call it hugging. And again, another advantage of the bending moment diagram is that you could see where it's positive, where it's negative. So you could have an idea by just looking at this diagram how a beam will be deflected. Right? You wouldn't know the values of deflection, but you could get pictures of what direction it's going to deflect in. Okay, so now we're going to talk about distributed load. Right? Before we looked at point loads, now we're going to look at distributed. And a distributed load is one that, as the name implies, a load that is spread out over the length of a beam. Right, so a good example would be those of you who have an upstairs and downstairs house, you have those concrete beams running horizontal. The load there would be the flow, because the concrete now is a uniform weight, but it's spread out over the length of the beam or distributed. Right, so point load is an ideal case. Right, if you really look at something like a point load, right, let's just say we have some mass resting on a beam like this. Right, we could approximate this to be a point load. But really, if you were to zoom in on this, you would see that it is in fact spread out over a region. Right, but to simplify things and all these analyses we're doing in strength of material, by the way, are simplifications and approximations, right? And a point load is one of those approximations. Now, there are times where we cannot do that. For example, the case with the concrete floor, we cannot make that approximation as a point load. So we have that as a distributed load. This example here shows for a unique case of a 3D printer on a 3D printed bed. Right, so this blue here is the glass bed. Right, so the glass has some weight to it, plus the weight of whatever we're printing. And then we have a power screw that moves the bed up and down. Right, we have some guide bearings here, not allow it to slide. If we look at it from the side view, this is how it will look. So we have a cantilever, we have the bearing, we have the glass bed, the support. This glass bed now is a distributed load over the bed support. So the bed support, or whatever structure inside that makes up the bed support, will have a beam. That will be a cantilever beam because it's cantilevered off with a uniformly distributed load, right? Or UDL, uniformly distributed load. Right, so we have distributed load and uniformly distributed load. Right, so if you were to draw this as a beam with our forces, this is how it will look. And if you look at the units for this load now, for a point load, the units are newtons. For distributed load, is newton per meter, meaning that for every meter you go, for every 1 meter you go, the load is W. Right, now, if it is we want to get the total load in this case here will be W times L. Right, and this would be newtons. Right, now, if I were to draw that total load on the beam, we have something called, this is the equivalent load. Right, so we can approximate it to be a point load. It's not the correct thing to do, but we could approximate it, and it will act where? It will act in the center because it's a uniformly distributed load. Right, so it will act in the center, right? Or as you will see as you move on in a few weeks' time, it will act at the centroid of the distributed load. Right, so for example, this is just kind of jumping ahead. If the distributed load were to look like this, like a triangle, it starts off big and then goes on small, then the equivalent load would act at the centroid of the triangle. Right, which in this case is 1/3 L, where L is the span. Right, but that's just jumping ahead a little bit here. Alright, so we could do a small example just to illustrate this. So let's say we have a cantilever beam, and let me draw this in black. Right, so we have a cantilever beam and we have a load acting like this. And this load is 10 Newton per meter. Distances, this is 3 meters, and the length of the beam is 5 meters. Alright, so in this case here, the equivalent load will be what? It will be 10 by 3, which is 30 newtons. right? And it will be acting at the center of that distribution, so it will be 1.5 meters. So now we could use that to calculate our reaction. So we have a reaction here, and then we will have a reaction moment. And we need a moment to keep the beam up. So our reaction moment in this case will be R will be equal to 30 newtons, right? Because that's equivalent load. And our reaction moment will be 10 by 1.5, 30 by 1.5. So that will be our reaction moment and our reaction force. So that's just a way on how we approximate the distributed load to be able to calculate our reactions. Right, so that is what these pages go. Right, so the distributed load, that in the example we did was a uniform distributed load, meaning that the profile looks like a rectangle. Right, but in the case of an aircraft wing, and we will do this later on, the distribution is not so simple. Right, we have a varying force, and that varying force is usually given as an equation. Right, this represents the lift on the aircraft wing. Right, in addition to this, we have the weight of the aircraft. Right, so if you look at the beam, the wing spar from a front-on view, it could be approximated to a cantilever beam with 2-point loads and a distributed load. Right, now we could even go further and go into 3 dimensions, where if you look at the aircraft from on top, right, so this is the wing. Remember, the lift force will be coming out of the page now, and you also have thrust. Right, so the equal and opposite, your thrust force from the engines will be pushing out like this, but you also have, right, so the cantilever wing spar will have loading in 2 different axes. You will have in the plane we see in this plane here, looking out, and then you will have it looking down. Right, but that's a 3-dimensional case, and we will do that in engineering design. Right, we won't do into that in strength of materials. Okay, so what we will do now, we will do an example that you could follow along. Alright, so we have a beam here, and we have a distributed load. It's a simply supported beam, right? Because it has 2 simple supports at the end, each end. And you want us to get the bending moment and shear force diagram. Right? We could find this at 1 meter intervals, meaning that for every 1 meter, you calculate the shear force diagram, the shear force value and the bending moment value. And so the first thing we need to do is determine the reactions. Right, so we need to get RA and RC. So like before, we sum the forces in the y direction equal to 0, and we sum the moments about some point equal to 0. So we could sum moments about C equal to 0, and we could say, okay, minus RA times 9, right? So that's RA here times 6 plus 3 is 9. Right, notice I've drawn the equivalent load here already, which is at 3 meters in the middle and 150 normal by 6. Right, so that's that plus 1500 by 6 by, that's 9,000. And this distance from here to here. It's 3 and 3 6. Right, so this will give us RA is equal to 6,000. And then we could sum the forces. Right, so we have RA and RC. Right, so we find the shear force and bending moment at 1 meter in the intervals. So first thing at x equal to 0, we know that the shear force is 0. Remember, it's free edge, and then we go up by RA, which is 6,000 on the graph. Right? Bending moment again is 0 at x equal to 1 meter. Right? What we could do, we could draw. We don't need to draw every time, but so just for simplification's sake, we have RA here is 6,000. This is bend the shear force, bending moment. And now on top here now, we have distributed load. Right, but remember we're only looking at a 1 meter span from here to here. And this here is 1500 Newton per meter, right? So the equivalent load will be acting in the center here for this little section. P equivalent. Right, and that will be 1500 times 1 because it's a 1 meter chunk we're looking at. And the distance it acting would be half of 1, which is 0.5 meters. Right, so we could do our shear force. Remember, always write this down, our directions. So shear force would be right, so that's our shear force at x equal 1. Our bending moment right, so we're taking moments about this face here where we cut. Right, so this should work out to be so that's at x equal to 1. Right? Next one, x equal to 2. Right, so again we could draw, let's say the hang of it, 6,000. Right, so our equivalent load, this is 2 meters. Our equivalent load 1500 by 2. And our distance would be 1 meter in the center. So you can see there's a repeating pattern here. Right, so we keep doing this for x equal to 3, 4, 5, 6, 7, 8, and then at the end, 9 meters. Right, so there's several times, but this will give you the practice. Right, so if you go on to the solution goes through 3, 4. Right, you could actually see now the graphs here. So it's at x equal to 0, shear force was 6, and at x equal to 2, remember it was 3000. So it keeps going like that. So we plotted each point. Then again, we have the bending moment diagram. Right, so if it's again something to note here where it crosses 0, you could see we have some maximum value there. Right, now, how do we know this is a curve? And this is a straight line. How we know that? Because remember, we just have points. This was at x equal to 1, the value for bending moment was 5250. At x equal to 2, it was 9000. Right, so why we doesn't go like this, straight lines. Right, so we plotted a curve through that, right? But how do we know? How can we calculate that equation of that curve? Right, and that is something that we're going to go into just now. Right, so this is how we look at a distributed load. In this case, a uniformly distributed load. How we find the shear force and bending moment diagram at intervals. Right, the next thing we're going to look at is, again, answering that question, this equation. How do we know it's a curve? Right, so we'll do an example with that next. Right, so we're going to look at the continuous method. Right, and again, the continuous method allows us to get an equation for those curves on those lines for the shear force and bending moment. So in this way, we won't have to be doing over this calculation for x equal to 1, 2, 3, 4. We just do it for one region at a time. And then we plot the equation for that region. Right, so we'll do it with that example. And what I want to do, or what I want you to do as an exercise now, is to determine the reaction forces RB and RC. The solution is given here, right? But you determine those reactions, right? You take moments about C, for example, solve for RB, and then you sum the forces in the vertical direction. Right, so let's just say we have RB, solve for RC is 3270. Right, so we want to determine the shear force bending moment diagram for this. I want to do the continuous method. So the first thing we want to do is we starting on the extreme left again, so that is here. Even though the support is here, we starting on the extreme left. And we want to break the beam in this region here, because we have the force, then we have nothing, and then after B we have this UDL. Right, so we want to break the beam here. And we're saying from here to here, the distance is X meters. Right, so we're doing everything in terms of x, and that's how we get the equation in terms of x. Right, so we could draw the simple block up until x, v, m. We have the force. So the force is acting down now, so our custom method acting up 1200. Right, and again we have our directions. Right, but we're doing everything in terms of x. So the shear force will be 1200 plus v. Right, so you notice the shear force is negative, meaning that it will not be pointing down, it will be pointing in the opposite direction. Right? And this here is valid between x is less than 1.2 meters, greater than or equal to 0. So this is the range at which this v is minus 1200. Right? That is this range here. At the bending moment, right, we're looking at taking moments about the n, and again everything will be in terms of x, so it will be 1200 x plus m equal to 0, m is equal to minus 1200 x Newton meter. And again, x is valid from 1.2, 0. Right, so that will be the bending moment equation between that two regions, between A and B. Right? The next thing we want to do is break the beam after B, because we have this UDL here. Right, so for this region now, we're doing it over now, this will be X now. Right, so we could draw this. Let's shade a little bit here so we can identify as part of the beam. Right, so this is A to B. Now we're looking at B to C. Right, so we have 1200. We have our B here, which is, and then we have a little piece of the UDL. Right, this is 2500. Now remember the distance from here to here is X. And the distance from here to here, this is A, this is B, is 1.2. So that means this distance here, where we break the beam, will be X minus 1.2. Right? And let's zoom in. The equivalent load will be 2500 into X minus 1.2. And the distance it acting will be what? From the edge would be X minus 1.2 over 2, or half the distance. Right, we have V and we have our bending moment M. Right, so we have our free body diagram for that section. So the shear force would be right, so many forces plus PEQ, right, plus V. As a V, we simplify this. Right, so remember you need to keep on top of the maths, the little algebra. Right, I would just be skipping over those steps. And this will be the shear force. Right, so we see the shear force now is a straight line, so it's a slant. Bending moment, right, so the bending moment, we take in moments about the end here, so it will be 1200 by x, right? We have this force here by the distance, so we clockwise will be minus, right? Plus equivalent load, which is 2500 by the distance. Plus m equals 0. Right, so that'll be our equation. Now, again, some algebra, we have some multiplication to do, and we'll end up with m equal to so that's our equation. Right now, all this here is valid between x is less than 4.2, right? That's our valid region. Right, so now that we have these equations for shear force and bending moment for these two regions, we could go ahead and plot these two equations. So you plot it like how you're accustomed plotting an equation. Right now, on Canvas, there and also at the end of the lecture here, the end of these notes, there's a link to a YouTube video as to how you could go about plotting this in Excel. Right, you could even plot it in MATLAB. So there's no need to really pull out a graph page and plot this. I will use the tools given to us there, which is Excel and MATLAB. Now, what if we want to find what is the maximum? Right? So what are the max values? So we could say, we know we have equation for V, so now we could get maximum. We could say dV dx equal to 0. Right? And that will give us the location location of max M. Right, so we could go ahead and look at the solution. Right, this is what we just now went through. And this is the shear force and bending moment diagram. Right, this was the equation for the first shear force, and then this was the equation again for that. Now you notice here now, when you're plotting this, you plot from 0 to 1.2. But when you start with the new equation, 1.2, you're going to get this value here, which is our jump. Right? Now this value, anybody could say what this value is here? That jump, you would notice that this jump here, this distance, is really 5430. Right? That is the up on the graph by term. Right? So it works out either way. Right? If you look at the bending moment, we could see here that the bending moment diagram, when they plot graph, minus 12 with x minus 12 means negative, so it will go down, and then you do the parabolic plot. Right, so if you look at this quickly, you can see that this here, this region here, we have negative bending moment. So this is hogging. So as one would expect, if you apply a load here and you pivot here, this beam is going to bend up like this, and then eventually it will bend down due to that load. So this is how the deflection of this beam is going to look. Right, so we could average now, based on that bending moment diagram, how the bending of the beam will kind of approximate to. Right, so lastly in this video, we'll look at cantilever beams, the continuous method. Right, now I'm not going to go through this calculation because it's the same thing repeating over and over. Right, in this case here, we have a cantilever beam. To calculate the reactions is given here, but you need to calculate it. Right, you take moments about A, right, and again, we apply our equivalent load here, which will be 30 kilonewtons by 2. Right, 30 by 2, and then it's be acting in the center, so the distance here will be 1 meter. Right, now, when we're doing this problem, you want to break the beam at some point here, and then we want to break the beam after. Right, so we're going to have two equations. One that encapsulates from A to B, and the next one that encapsulates from B to C. Right, so for A and B, right, this is the region here. Right, we could draw in here, just for completion's sake, we could draw in our UDL. Right, for that distance here. Right, I have already any solution, I just had the equivalent load. And then you could see here for the bending moment diagram, or for the bending moment value, we have MAB, that is anti-clockwise positive. We have the distributed term, 30x by x on 2, right, because the distance here is x on 2, right? And then we have plus 70, right? That is the reaction moment. So that is an applied moment to the beam that keeps the beam in equilibrium. And you can see that is anti-clockwise, so it's positive. And then minus 64x, which is that direction, 64 by x. And that will give us the bending moment value or equation. We do the same from B to C. Right, so this is how this would look. Right, so if our UDL, you would always have some straight line for your shear force. And you would always have a curve, a parabolic curve. You notice where the UDL stops now, then we end up with a straight line. Here in this case, we end up with a flat line for your shear force. Bending moment is negative, so that means as one would expect, this beam is hogging. So it's bending down like that. Right, so we would stop here, and the next week we will start to look at the integration method, which allows us to take this equation for this distributed load, right? And I'll go back to this example here with the aircraft. So you have this big equation here, and with the integration method, we could just integrate or differentiate as the case may be. We will see what we're going to do, and that will give us the shear force equation and bending moment equation. So it's pretty simple. Integrating equations like this is very easy, right? And that will allow us even down to getting the deflection of the beam, an equation for that. Right, so we'll touch on that next week.